Good day, grade 12 chemistry students. Today what we're learning about is valence bond theory and hybrid orbitals, how to draw orbital overlap diagrams. We're specifically learning about how this relates to double bonds and triple bonds in hybridization. Okay, so we're going to look at the periodic table now, and remember we have a couple different zones here. We have the S, P, D, and F zones. We're going to focus on hybridization as it relates to BF3. Now recall BF3 breaks the octet rule. It actually is satisfied with 6 valence electrons, so it is breaking the octet rule. Other ones that will break the octet rule are less than the CNOF ones, like beryllium will be actually satisfied. So to start with this diagram, what we're going to do first is we're going to show the energy level diagram for boron. And if you look at boron, it actually can only make one bond according to the energy level diagram. It's only got one lone electron. So when we draw the Lewis structure like I am right now, you can see that it has to form 3 bonds. So in order to form 3 bonds, what has to happen is we have to form a promotion. Now a promotion occurs so that we can make 3 bonds. So one of our electrons is going to be promoted up, and you can see it's being promoted right now. Now I have 3 bonds, but the issue is that you have each one of these 3 bonds has to be the same. So I have an S and 2 P's. So what ends up happening, so we have the same type of bonds for all 3 fluorines, is that we have a hybridization. So the 3 things come together and they hybridize, and they form sp2 hybridization. Notice how one of the P's that was left over, it actually is higher energy, and this is now sp2 hybridization. So as you can see that again the S increased in energy, the P's decreased, and so you have sp2 hybridization. So one S and 2 P's came together to form sp2 hybridization. Now, what shape is this? The shape that this is going to form is called trigonal planar shape. The angles that it's going to have is 120 degrees between them. So trigonal planar means that it will fit on a flat plane surface. So if we're going to start by drawing boron, and I'm going to show you the hybridized orbitals, and it's got 3 of them, and they look like bowling pins. And the angles between them are 120 degrees. So it's sp2, and the angle there is 120 degrees. So when we look at fluorine, we draw its energy level diagram, and we look at it, and it's 1s2, 2s2, 2p5. We can see that it has a 1 half-filled p orbital. So the way we draw that, again, is it looks like a dumbbell. So we got 3 fluorines around. And we're going to draw a dumbbell off of each one of those fluorines. And we are going to put an electron from each orbital in there with opposite spins. That is a end-to-end bond. That's called a sigma bond. And we have sigma bond at each location there. That's 120 degrees. So as you can tell, guys, the energy level diagram here, or the hybridization, is really showing us that it's showing us how it's breaking the octet rule. Okay. So another example would be BeCl2, which you'll see has Sb hybridization. We'll try that one in class so you can understand it a little bit further. But that will have a linear shape, and it also breaks the octet rule. So next what we're going to talk about is how valence bond diagrams explain double and triple bonds. And the way they do it is through a process called hybridization, where orbitals come together and they hybridize. So what we're going to do is we're going to start with an example with C2H2, C2H4, and it's known as ethene. So when we draw the Lewis structure, we're going to look at it, and you'll see that it has a double bond. Now each carbon is bonded to 3 atoms, 2 hydrogens and the other carbon, but it's double bonded to the carbon, and this is known as a pi bond. We'll explain what this means. So we'll have some normal bonds in here, some sigma bonds, but we'll also have some pi bonds. So to understand this, we have to draw the energy level diagram for carbon. So when we draw it, it's 1s2, 2s2, 2p2. You can clearly see that we actually have 2 orbitals that are half-filled available for bonds, but we need to make 4 bonds because we have a double bond and we have 3 atoms there, but between those 2 carbons we actually have to make 2 bonds. So it's 1 between the carbon and hydrogen, a second between the carbon and hydrogen, and then 2 between the 2 carbons. So whenever you have a double bond, that means you have a pi bond and a plain old sigma bond. Now pi bonds are known as side-to-side bonds, and they're going to be made by a half-filled p orbital. So pi bonds happen between p orbitals. So let's start by making sure that we can do 4 bonds. So we promote an electron up. We now have 4 bonds available, but 1 is an s and 3 are p's, and we need to know that if we're going to hybridize, in this case we're going to just do sp2 hybridization because we need to bond to 3 separate atoms. So we're going to just hybridize 3 of our orbitals, 1 s and 2 p's. We'll do sp2 hybridization, which means we have a trigonal planar, and we'll have 1 p left over to do our side-to-side pi bond. And so the leftover p orbital right there that I've just asterisked, that is going to form my pi bond. We can actually label them px, py, and pz. Pz is going to be the one that's left over, and that's the 2s1. So the ones that hybridize are the 2s, the px, and the py. I will explain why, but we want to get that trigonal planar that's just on a plane, and we have a pz that's left over half filled. So let's take a look what happens. We're going to form, the energy between these is going to decrease. We are going to get a new type of orbital called the sp2 hybridized. Now why is it sp2? Because we have 1 s and 2 p's coming together. So you can see in green there we have sp2 and we have 1 pz that's left over half filled. Now when we draw this out, we'll take a look and you're going to see that we are forming a trigonal planar shape. Now the trigonal planar shape again is going to have angles of 120 degrees. Now there's 2 carbons, so therefore they're both going to have 120 degrees. So we'll start by drawing our bowling pin like hybridized orbitals, the sp2 hybridized orbitals, and they're going to have 120 degrees between them. So it looks a little bit messy, but that's leaving the carbon atom. Those are the orbitals. That's the shape. We're going to do the same thing off of the other carbon, so sp2 hybridized. So let's go ahead and do the same thing off the other one. 1 electron in each. Oops, sorry there. And let's do the same sp2 hybridization off our other atom. And you can see that I've added an electron. Now what kind of bond is that? That's an end-to-end bond. That is a sigma bond, and we have 1 bond between our 2 carbons. Now because we have this double bond, that double bond is going to happen from this pz, which I'm not showing. Now each carbon has a pz that's actually coming out of the plane. So I'm going to put dotted lines to show that it's going out of the board and going into the board, or out of the screen going into the screen. And that's a pz orbital. And that is also half filled, so let's put an electron in there. And we also have another pz coming out of the other carbon. Now, though this is kind of misleading because these pz's are actually overlapping. And there is a pi bond. This is what the pi bond is. Now that's 1 lobe of the p orbital, but we also have another lobe on the opposite side. So that represents 1 pi bond that's existing there, even though I'm showing 2 arrows there. That is 1 pi bond and 1 sigma bond. That makes up a double bond. We're going to find out that this causes the molecule, single bonds can rotate, but we're going to learn that double bonds are unable to rotate because of this double bond. Now our molecule isn't quite, because we still have those hydrogens on each end of the carbons. At both ends you have 2 hydrogens bonded there. So they're going to be bonded to the sp2 orbitals there. And if you recall the energy level diagram, for each one of those, hydrogen is 1s1. So we're going to just put an s orbital and put an electron in there. What kind of bond is that? That's going to be a sigma bond because it is an end-to-end bond. So we label each orbital, the blue orbitals are s orbitals, and we have 4 sigma bonds, and we have, so 4 sigma bonds for those hydrogens, and we have our molecule. So this is the energy orbital overlap diagram for ethene. Okay, so just to reiterate this a little bit more, we had a leftover PZ, and that forms the pi bond. Sometimes you'll have, like carbon, it will hybridize either sp3 if it has 4 separate molecules or 4 separate atoms bonded to it, sp2 if it's bonded to 3 things, or sp hybridization. You can see here that we have three different atoms bonded to this carbon. So therefore, it's going to undergo what we call sp2 hybridization, and you can see it quite clearly here. The shape is trigonal planar, and what happens is they form a sigma bond, which is an end-to-end bond right there in the center. Recall that when we did the energy level diagrams for carbon, we had some leftover pz orbitals. So we have the hydrogens doing sigma bonds as well, but on that carbon atom, each carbon atom, we have 2 pz orbitals that are left over, and there's 2 lobes there on the top and the bottom. So those electrons exist in both of those simultaneously. We don't know where they are. We know they exist in both. It's got 2 lobes. That's 1 pi bond. So 1 sigma bond and 1 pi bond is actually what a double bond looks like. Okay? So we're going to see this a little bit further as we continue this in class. Thank you very much.
Who sleeps in best when you've got the sunrise? Wasting time watching infomercials live on Channel 9. Us and Billy Mays. No